Hey guys, welcome back to chapter 16. So I left you guys with this thought about the Arrhenius definition. So Arrhenius definition defines acids and bases with respect to aqueous solutions. So what happens when we put them in water? What if we're not dealing with an aqueous solution? What if we're not dealing with water? So enter the next definition. That's the Bronsted-Lowry definition. And this is going to be the area that we spend most of our time in for the next couple chapters. So the Bronsted-Lowry definition focuses on the transfer of a hydrogen ion during some sort of chemical reaction. Very often, chemists will refer to hydrogen ions as the transfer of a proton. So you'll hear words like proton donor, proton acceptor. Remember when we looked at this idea of a hydrogen ion? A neutral hydrogen atom is one proton, one electron. When this hydrogen atom becomes an ion, it loses that electron, and what's left? Yeah, it's just a proton left. So very often you'll hear this ion referred to as just a proton acceptor, proton donor. Okay. So according to the Bronsted-Lowry definition, an acid is going to be a proton donor. It's going to be something that gives up a proton during a chemical reaction. The way that I remember this, so I have the silliest ways of remembering things in chemistry, but it seems to have worked for me. I see this D in proton donor, and I link it to that D in acid. So I say acid proton donor. So that D and D are how I connect those two in my brain. A base, on the other hand, is going to be a proton acceptor. And again, I see this A, an acceptor, and I see the A inside of the word base. So accept base. That's how I connect those two. So when we start looking at chemical reactions, the base is going to be something that accepts a proton. The other thing that we're going to see with a base, so in order for it to accept the proton, that base is going to have a lone pair contained somewhere on the central atom. So for example, we could use water. So water does have basic properties sometimes. So in order for something to act as a base, it has to have this lone pair on the central atom so that when it comes into contact with this proton, that proton has somewhere to latch onto. So that's going to be something else, a little bit more advanced than Gen Chem 1, but certainly something you'll use again in organic, is it must have a lone pair. Okay. So proton donor, proton acceptor. So let's look at some examples here. So here we see that we're using hydrochloric acid again. So no surprise here what this is going to act like. It's going to act like an acid. So we're going to mix hydrochloric acid with water. Okay. In this case, if we're mixing these two together, something has to be acting as an acid. And if something's acting as an acid, the other guy has to be a base. So what we see here is that hydrochloric acid, HCl, is going to be our proton donor. So it's going to give away that hydrogen atom. And we're going to link it on the other side to this chlorine ion. So we see that it started as HCl and it ended as just Cl. And what's the difference between those two? Well, the hydrogen was given away. It was donated to somebody else. Okay. In this case, if HCl is acting as our acid, then our water must be acting as a base. So remember, bases are proton acceptors. Okay. So we're going to link our base water over here to the H3O. And what's the difference between H2O and H3O? Yeah, it accepted an extra hydrogen. So hydrochloric acid, HCl, donated a proton. Water accepted a proton. Okay. So this link that I made on opposite sides of the reaction arrow, they have names, okay? So we're going to call them conjugate acids and conjugate bases. So over here, HCl was our acid, and it is linked to its conjugate. So it's always going to be called a conjugate. And an acid will always be linked to the conjugate base. Okay. And here we see that water is acting as a base on the reactant side, and it is also connected to his conjugate, but this conjugate is going to be the conjugate acid. So things always appear in acid-base pairs. So acid, conjugate base, base, conjugate acid. Okay. The other thing to point out here is, as I mentioned at the beginning, these definitions of acids and bases just get more inclusive. So here we see hydrochloric acid being put into a beaker of water. So we're still using an aqueous solution here, but we can also define hydrochloric acid as a Bronsted-Lowry in that it donates a proton. So even though we're still in an aqueous solution, this is a valid definition. It still fits the mold as being an acid. Okay. Oh, and I have all that in there. So here's our example of ammonia, NH3. So I said sometimes our bases don't inherently have that hydroxide ion looking at us in the face saying, oh, that's definitely a base. So we're going to look at how NH3 here does in fact act as a base and how we can define it using Bronsted-Lowry. So in this case, NH3 is going to be our base. Well, how do I know it's acting as a base? Well, I'm going to look for its conjugate pair. So here I see NH3, and over here I see that NH, and now it's NH4. So going from NH3 to NH4, what did it do? It accepted a proton, right? NH3 to NH3 accepted a proton. So that's how I know that it's acting as a base. So NH3 is the base, and it's connected to its conjugate acid. Well, if NH3 is acting as a base, what must water be acting as in this case? Yeah, it's got to be acting as an acid. So let's take a look at that. Here we see H2O, and it must be connected with this hydroxide ion. So what's the difference between two hydrogens and an oxygen and one hydrogen and an oxygen? Yeah, it donated or gave away a proton, a hydrogen. Okay. So water is acting as an acid, as a proton donor. And over here, we've got its conjugate base. Okay. So while NH3 didn't inherently have that hydroxide ion staring us in the face, when we put NH3 into water, it still produced a hydroxide ion. So again, this guy's defined from the Arrhenius definition, so increase the number of hydroxide ions. And it's also fitting into the Bronsted-Lowry, where it accepts a proton. Okay. Something else to point out here is I've used water twice now. So in one example, I used water as an acid. In one example, I used water as a base. Water is one of those rare chemicals that can be used as an acid or a base, or act as an acid or a base. We call that amphoteric. So it's one of the very, very few molecules that can do that, but it's important to note that it can, in fact, do that. So here in this slideshow is where I actually go through this idea of conjugate acid-base pairs. So this is everything that we've already talked about. So we've got an acid reacts with a base, and it will always be connected with its conjugate pair on the other side. So acid, conjugate base, base, conjugate acid. And then this is just breaking down those conjugate acid-base pairs, showing you that NH3, the base, is attached to NH4, the conjugate acid. And why are they attached, or how can I attach them? It's either the addition of a hydrogen or the removal of a hydrogen. So that's what makes these conjugate acid-base pairs, is they either accepted a proton or they donated or removed a proton. Okay. So let's try a few. Let's look at some. So I want you guys to look at both of these reactions, reaction 1, reaction 2, and I want to see if you can correctly identify all of the conjugate acid-base pairs. So for a question like this, I'm looking for 4 correct answers. I'm looking for the acid, I'm looking for the base, I'm looking for the conjugate acid, and I'm looking for the conjugate base. So get 4 words onto the screen. All right, so let's look at this first one here. So let's say that you don't automatically recognize this as an acid or a base. So you're going to take this and you're going to connect it to something on the other side. That's the addition or the removal of a hydrogen. So we've got the SO4 polyatomic, SO4 polyatomic. So here's our pair, okay? So what's the difference between H2SO4 and HSO4? There has been a hydrogen that has been removed. So this guy donated a proton. Proton donor means that this was the acid, and this must be the conjugate base. Okay. So if that guy was acting as the acid, that means the other one is acting as a base. So this must be acting as a base. Let's prove that to ourselves. So what's the difference between H2O and H3O? It accepted a proton. Okay. So if water was acting as a base, this must be its conjugate acid. The next one, a little tricky here. So you might have looked at this and said, oh, it begins with a hydrogen. It must be an acid. So then you linked it to the other side. So we see this CO3 polyatomic, CO3 polyatomic. What's the difference between HCO3, H2CO3? Yeah, this guy accepted a proton, right? Oh, so this guy must have been the base. And this is the conjugate acid. Okay. So if that guy was the base, then water must be our acid. So what's the difference between H2O and OH? Yep, it donated a proton. Okay. So water was our acid, and then hydroxide is our conjugate base. So an important skill, something that you really need to test yourself and start being able to flip back and forth and look across an acid-base problem, you are going to need to be able to recognize conjugate acid-base pairs. It's just going to make life much easier as we move through this chapter. Another thing I'd like to point out, just one last thought here, is these conjugate acid, conjugate base. They are called that way for a reason. So this conjugate acid over here does in fact have acidic properties. So if we were to look at the inverse or the reverse, it would in fact have an acidic property. Same thing with this conjugate base. If we were to look at the reverse or the inverse, it's going to have basic properties. So we don't just arbitrarily throw this idea of conjugate acid, conjugate base name on there. Those names are there for a reason. So that's it for Bronsted-Lowry. I hope you guys found this helpful.